from homographs. For example, the noun permit versus the verb permit, the noun record versus the verb record. And versus prosody could also help differentiate the focus of a sentence. So the entity, which basically what entity of the sentence is more important. In the two instances here, like Mary went to London last week versus Mary went to London last week, you can imagine that these two sentences are answering quite different questions. In the first case, you're probably answering the question, who went to London last week? And in the second case, maybe you're answering, where did Mary go to last week? So yet on another level, and this is more popular or more common and more well studied in the sentiment and affective computing, is the disambiguation of sentiment. So again, the same sentence that looks the same on paper could be the difference between yeah, sure, versus yeah, sure. Something that's lukewarm versus something very enthusiastic can be differentiated by prosody. And then we'll focus on these last two cases of one's a differentiation of intent and syntax. So for that, for example, in intent, it's the prosody relationship to syntax and meaning. The motivation here is that, as it turns out, the prosodic boundaries align well with syntactic boundaries. And in meaning, prominence or something that's more salient in a sentence, that together with intonational cues can signal entity importance and intent. So in this example, you want coffee versus you want coffee. It's as speech people, I think you've probably cited this example multiple times as well, where you have rising pitch signaling question and a lowering pitch signaling statement. So again, you want coffee? You're asking if they want coffee, or you want coffee, something like that. And then with another example, Mary knows many languages, you know, versus Mary knows languages, you know. So I guess if Mari was here, she would say that I did that prosody pretty poorly, but I'll try it again. So in the first case, Mary knows many languages. Mary knows many languages, you know. So in the first case, you have a pause there, and then the you know is essentially a parenthetical. It doesn't really add to the meaning of a sentence, but it's a common communicative device, or is a phrase that is said a lot in conversations. And in the second case, Mary knows many languages. Mary knows many languages, you know. The you is more prominent. You don't have the pause there, so it signals the structure of a sentence. It's more something like the you know is a subordinate clause that tells you that Mary also that Mary knows many languages that you also know. So the same sentence may be written the same way if you ignore the punctuations for now. Have two different meanings again because of the syntax and the structure of a sentence that was most likely you as a listener could differentiate based on listening to the prosody of the sentence. So more formally, in linguistic studies and earlier work in prosody, it has been defined on two levels, the symbolic and the acoustic level. On the symbolic level, people have focused on looking at the prominence, which is the relative salience of elements in the sentence, and then phrasing, which is the grouping of these elements, and how these are exhibited in speech based on the acoustic cues, and in particular in patterns of energy, timing, and intonation or pitch. So, for example, the increased pitch range or loudness can signal emphasis. So these are the acoustic cues that signals that maps back to the prominence of the elements in the sentence. And then pauses and lengthening usually signal phrase boundaries. They happen most often before phrase boundaries. So they also, so this is the correlation between acoustic cues and the phrasing level in the symbolic level. So we've seen from these examples that it's actually very common in human, and you probably don't even notice that you're using these types of cues to communicate. But it's actually been not very well used in natural language systems. And one reason for it is that the acoustic cues and phrasing to signal prominence and phrasing, these collisions happen on the individual level as well as in combination. So the mapping between the acoustic cues and the symbolic level, it's not a one-to-one mapping. There's a lot of things happening, not to mention all the different variances happening in speech, as I'm sure this audience would know. So it's not always the most straightforward to make efficient use of prosody. And so this is the prosody referenciation from the common annotation system, TOBI, Tones and Break Index. This is one, in traditional, in earlier work, when people study prosody, this is the kind of annotation that people were looking at. So this example I took from an open course at MIT, actually. It's basically a class on teaching people to annotate these types of representation in speech. And you can see this, this is the sentence.
Who was it, Melanie?
So some of the sounds are kind of not loud enough. So please turn up your volume if it doesn't, if you can't hear it very well. So, yeah.
Who was it, Melanie?
So the way that people have worked at this is there was a definition of the tone tier, which have the symbols of H for high and L for low. And then the break index tier, which has annotation from 0 to 4, signaling how much disjuncture between the elements of the sentence is. So 4 signals this is a phrase boundary, as you have heard from this.
Who was it, Melanie?
And then the high and low annotations of tones here required some experts to both listen to the signal, and there's also the spectrogram here with pitch tracking, where they could make use of the actual F0 contour, and the annotations were done in that way. So this is actually a relatively tame example with only these 4 types of tone annotations. And as you can see, in this one, it's a much more complex example with P actually denotes some sort of disfluency that in this system, the expert annotators were asked to annotate. So the samples is like this.
Display all the flights from Baltimore to Dallas, which leave after 4 p.m.
So there was some slowing down, some pausing that you might not expect in a more fluent conversation, but it's still fluent. It's not like the person hesitated or adding filled pauses like uhs and ums, but it's still.
Display all the flights from Baltimore to Dallas, which leave after 4 p.m.
Yeah, so it's not something that it's an utterance that you would think this person is saying, and at the same time still planning to say what's going to happen next. So as you can see, if I didn't know that this was maybe a conversation with a flight booking agent, for example, then I think that this maybe there's nothing wrong with it, or maybe for a non-expert linguist to listen to this, you might not necessarily think that some of these are hesitation and disfluencies. So anyway, the point is that it could get pretty complex. The annotation does require some expert knowledge from linguists, so it's definitely going to be expensive, and it's not always well agreed upon, even if the case seems like a pretty clear-cut case, and it's also not available in all languages. So the prosody framework here that we have is served more as a motivation for us for what kind of features that we're going to look for and try to represent in our models. but we try to move away from using this kinds of annotations, as it's not going to be scalable when we work with different types of speech and language data that we have. So, and formally, the challenges that I saw in working with Prosody and natural language processing had the problem from the modeling aspect and the data aspect. From the modeling aspect, as we've seen before, mapping a prosodic function and the acoustic cues is complex. So it's not straightforward how you would do this. And there's also the difference between having discrete words and continuous speech. So the point here that I mentioned discrete words versus continuous speech is because we've seen lately in NLP, there are a lot of advances that have all these different types of architectures and models that do very well on different NLP tasks, but it's not really clear to us how that could be applied to data that's more conversational and based on speech. And then from the data perspective, by definition, prosody is not seen in this transcribed words. So if you have something that is not seen, how do you make use of it or learn from the labels if the labels are all based on the transcripts mostly? And then there's also the question of how much speech data you have compared to text data. For speech data, it's not something like you can crawl on the web. And there's also issues with privacy and security that I'm not getting into here yet. And then there's also the difference between transcribed text. Is it whether you have access to that kind of perfect transcripts versus ASR data? You get some from the system, and that again is also different from written text that you maybe get from even internet forums or books. So the style is also different. So the style not only is different on the written text versus transcribed text or ASR text, but there's also the style difference on the acoustic level between spontaneous speech and read speech. And we'll go over that in the few next slides. So in my thesis work, we proposed to work on these challenges by the modeling based on neural models, as it's somewhat a more appropriate way to combine continuous speech representations with now more continuous representation of discrete text, in particular word embeddings. And then for the data problem, we focus on expressive and spontaneous speech. And as we'll see, it's more robust, and it's frankly more interesting with all the different types of prosody and the speech types that people generate. So in my thesis, I focus on two tasks. One is the constituency parsing task and dialogue act recognition. Constituency parsing, this is the task of identifying utterance structure. Given a sentence, we would like to get a representation of its structure, like this is a constituency tree, where you have under a sentence node, you try to identify which words fall under verb phrase or noun phrase, and so on. And this is motivated by the fact that prosodic boundaries align with syntactic constituent boundaries, so you can make use of signals like pausing, lengthening, and so on to identify which words or entities fall under certain constituents. And then for another task that we look at was dialogue act segmentation and prediction. So I'll refer to it for short as dialogue prediction, but it also involves segmentation. So we try to identify an utterance intent, but also in doing that, we also identify the utterance boundaries. So this is motivated by the fact that, again, prosodic boundaries align with utterance boundaries, and then intonational cues signals intent. So specifically, the task that we're looking at here is, for example, if you have a sentence like, yes, I love cats, the output that we want is to have it segmented by So these yes falls into one utterance, and then I love cats and another utterance, and then we also want to identify which dialogue act each of this belongs to. So in this case, this is the answer to yes no question, and this would be statement opinion. This is all based on switchboard annotation. So the general framework that we're looking to here is a general encoder decoder framework. For the encoder, try to learn useful input representation, and in all our models, we use the input at the token level. For the decoder, it would learn to do task predictions, in this case, token or utterance or higher level based on whether it's a constituency parsing or the dialogue act prediction task. So the big question here is how should we deal with the speech signal? And in particular, how do we make good use of prosody? And for that, we use an automatically learned representations. But before that, some of the previous work or the common representations for input that were looked at. And here we actually assume that we have transcripts. So at least some sort of word text representation of the utterance. In previous literatures, you can have all these types of word embeddings. In older days, there were non-contextualized embeddings like love or latent semantics allocation. And then later you have representations of the different tokens by the hidden states of neural networks. And then what we discovered recently is that contextualized embeddings is also really helpful, even though they were pre-trained on large text data. So again, this result was actually pretty surprising because again, the mismatch between style of written text that you see on the data that these word embeddings were trained on versus the conversational style of text or transcripts that we have for switchboard data. And then for prosody, as I mentioned previously, people have looked at the Toby annotation, whether it's gold standard annotation from certain data sets, or people also try to get silver annotations by training a system to predict these Toby tone and break index labels, and then apply that to their data sets. But again, we're trying to move away from that. Some approaches also use word level summary statistics. So if you have a word that spans multiple frames, you can do some averaging or max pooling of the acoustic features from those words, and then use that as a feature for the word to represent the word on the acoustic level. But this approach doesn't really capture the changes within word. And as we've seen in the pitch contour of those examples, it's it could change a lot within even within a word. So we want to try to learn some better representation of these changes on the acoustic level. So our prosodic features were motivated by those previous studies on how prosody is represented. And in particular, we use energy and pitch-based features, as these were shown to capture articulatory strengthening at prosodic constituents onsets. And then we also looked at pause and duration features, as duration features, in particular word final lengthening, could be cues to prosodic phrase boundaries. So that, in combination with word embeddings that's now ubiquitous in NLP task, and we combine that into a convolutional neural network learning framework, and then that gets concatenated. So basically we're doing early fusion. Everything is done on the word level. So the word gets the word embedding representation, and and then we summarize our frame-based features on the with all the acoustic frames on the word level. And then these CNN filters will potentially capture the changes on the word, subword, as well as the context level to be used in concatenation with the word embeddings to do the prediction task. And this is all learned jointly with the downstream task. So coming back to this picture, we'll fill in this general encoder-decoder framework with the CNN module, where we learn the representation of prosodic and acoustic features, and then do everything is learned with the prediction task, depending on constituency parsing or dialogue act prediction. So the first set of results that I'll talk about here is in the constituency parsing problem. You can, so on the input sentence representation, it's relatively more straightforward to see how you can approach this. The input is a sentence or a sequence of word level features, where you have word embeddings concatenated with those pause, duration, and learned CNN features. On the output side, we explored with several models that were state of the art at the time. It's based on how the output is represented. So on the one hand, you can look at this constituency tree as a linearized representation, where you traverse the tree and write out all the different nodes. So you start with an S node and then edited node, and then keep writing this down. So it's essentially a linearized parse symbols, sequence of parse symbols, and that can be formulated in the sequence-to-sequence problem, and use that as our parser. And then another representation that has become more popular later is the span representation for learning the parse tree. So the representation for that tree, there is the span representation of tuples of the labeled constituent and the starting and ending indices of those constituents. So for example, here you have these S node starting from, so actually this should be more than 5 because this is spanning 8. So, or the edited, so this would be S from 0 to 8. And then you write down what the edited constituent spans. So it spans from index 0 to 2 and so on. So the thing to note here is that most of the constituency parsing problems have been studied on written text. As again, that's where the typical or the most standard database for that is the Wall Street Journal database with tree banks. And it's not really straightforward or obvious that all these parses that were learned or studied on this data would do equally well on our switchboard data set because of things like dissonances and fill pauses. When, for example, in the dissonancy here, or referendum is a note that represents something the speaker said, and then later correct themselves, and then keep moving on and say the rest of the sentence. So the sentence would be something like, and that, and they stopped, they corrected themselves, and then say the rest of the sentence. So you can also think of it as if you remove the whole edited node from the parse tree, the rest of the sentence will have its same meaning and nothing really gets affected. But it does get, but there are cues and different signals to say that this node or these two words behave somewhat differently from the rest of the sentence. So so that's something that we wanted to explore and see, do these parsers that are doing really well on written text, how are they doing on conversational speech? And the evaluation that is usually done on constituency parsing is the F1 on the tuples of the constituent label starting and ending index. So the neural parsers that we looked at, one was the sequence-to-sequence model. I guess everything is sequence-to-sequence now, depending on how you formulate the problem. But at the time, it was the sequence-to-sequence. With the RNN encoded decoders. So that was, so this is the linearized representation where you have input sequence and then linearized sequence of parse symbols. And then the self-attention model is the newer one with the transformer encoder, and then the span-based chart decoder. So if you're familiar with PCFG parsing, this is essentially a CKY parsing where the scores of each cell is based on a neural network instead of the probabilities of grammar production rules. And this could be solved by a dynamic program once you have all the scores filled in the cell, and the tree can be reconstructed that way. And in both models, we use our CNN module to see how Prosody could help with this task. So the parsing results here, the main questions or the main results to highlight here are that the model with the transformer encoder, so self-attention, outperformed the sequence-to-sequence model by a large margin, even with, so the first row here is a sequence-to-sequence model versus the third row self-attention model, and this is word embeddings learned jointly. So there's no pre-training of the word representations. As soon as you add some sort of pre-trained embeddings, even though this is non-contextualized, the results improve. But again, the model with self-attention or the transformer encoder, again, outperformed the sequence-sequence model. And then once we add the pre-trained contextualized embeddings, the performance is even better. And so this is actually, like I kind of alluded before, this is a result that we weren't really sure we would get, because BERT or Elmo or any types of the pre-trained contextualized embeddings were all trained on written text data. It's not necessarily conversational data like switchboard that we have. So it was a pleasant surprise that it did so well on the switchboard data. And then once we add Prosody, we have, again, better improvement. Again, so this is a slight improvement, but statistically significant. It's also much harder to get improvements once you're in the 90s. And again, the transformer encoder does better, and and even though BERT is already a strong baseline, adding Prosody still helps. So this is one example of where Prosody was most useful. Most of the signals that we get from Prosody help with types of attachment errors and dissonancy related errors. So in this example, the left parse tree was found by the text-only parser, so no Prosody was used here. And then on the right is the parser that does make use of Prosody. So the sentence originally was, we tried to put away 2 and 4,000 and so on. So the annotation here means tried away is a dissonancy or the referendum to be corrected. So the person said, we tried away, but then they corrected themselves, and what they really wanted to say is, we try to put away, and so on. So the parser that does not make use of pauses, for example, put the edited note under VP here, and it missed that this is actually an edited or disfluent constituent, versus the parser that can make use of the pause, correctly identifying that this is the edited note, and therefore avoided the attachment error with VP constituent. So another interesting set of results that we looked at was the style mismatch between read speech versus spontaneous speech. So here we looked at switchboard. The columns, the left here is what data we trained on, C for conversational and CSR for read speech. And then on the right, we have where it was tested on. So again, C for conversational and R for read speech. And for read speech here, we have the data set. This is the read news data from a different subset of Wall Street Journal that we tested on. And then the top 2 rows are just using transcript, and bottom 2 rows just using transcript plus Prosody. So the stuff on the diagonal should be the high score, because you are testing on the same style as the training, versus the stuff off the diagonal is where you train on read, but then test on conversational, or train on conversational and test it on read, and without and with Prosody. So the first thing that we notice is that when you train on conversational and then test it on red speech, there's some degradation in performance, but it's very small compared to the other direction, where if you train on the red style of speech and then test it on the conversational speech, the performance dropped a lot. And then so that kind of indicates or suggests that somehow training on diverse prosody or the conversational style of speech is more robust to this kind of training and testing. And then there's also the comparison whether you do use prosody in both cases or not using prosody. So if you are training on conversational speech, and then you add prosody. In both cases, whether you test on conversational speech or test on red speech, prosody still helps. Versus in the other case, if you train on red speech, adding prosody in the same using training on red speech but testing on conversational speech, you don't get gain, or maybe the performance slightly drops. Versus if you train on red speech but test on also red speech, then in that case prosody helps a little. So this kind of suggests that the style mismatch for these types of training parsers is both in terms of words, so what is being said in the what's being written or said in the data, versus how it's being said in the conversational data versus the red data. So this is a good point to ask questions if people have any. Again, feel free to just unmute yourself, I guess. The result for this part is that the transformer encoder and chart decoder for parser plus some sort of pre-trained embeddings, in this case we use BERT, really did give our good performance. When you add prosody, the main benefit was reducing attachment errors and misdissonancies. And then in the speech time mismatch effects, we saw that the parser trained on conversational speech is more robust, likely to the more diverse prosody in it. And therefore, it's important to look into to use conversational style of speech instead of just using red speech, for example. So this was the first part, the first set of the first task. Now, for dialogue act prediction, the setup is similar, except the output is now we're looking at a tag sequence, essentially. It's because we're looking at also both segmentation and recognition. We basically looked at it as a sequence, tag sequence prediction, so sequence labeling. Again, we have input is a word sequence, a sequence of word level features. So again, we'll use word embeddings and all the pausing and acoustic learning from the CNN module as our input. And then at the output, to have some sort of segmentation signal, we tag each token in the sentence with I for not being at the sentence boundary, and then E with underscore the dialogue act tag to represent the segmentation, and then the dialogue act that's associated with that segment.
Trang, there's a question, so maybe you want to take it before we move on.
Right. Thank you for the talk. I mean, it's very amazing. But I have one question regarding this embedding, which you have. XI is where you have an embedding, and the SI, I think, is the speech property, like F naught and energy features. Can you tell me a bit more about this FI? How do you, what is FI more in a little more? Like you said that it's duration feature. How do you model it, like a little more, like how do you actually, it was present in the data that how long this phone or this sound is made, or you jointly modeled it along with when you were training the model?
So the phi, so the SI is the output of the CNN with energy and pitch features. And then the phi is the pause and the duration. So duration, we just use, we have timing, we have time alignment on the word level. So we can use the duration of each words based on the difference in time, start and end times of those words. And we also did some normalization based on the data statistics. For pausing, we use a quantized pause representation. So again, it's also based on the time alignment. So just seeing the difference between start and end time of the previous word and start time of the next word. So those are all scalar features. So those were not frame based. So you wouldn't have to use CNN for that.
Right. Cool. Thank you. Thank you.
Thank you for the question. So for this, the evaluation that we're looking at is now an error-based measure, where the DSER is a segmentation error rate, and DER, DA error rate. And then we also have a label error rate where, so the DSER is more focused on how it gets segmentation correct. And then the two other measures were more focused on the actual label of the dialogue acts. So in this case, for example, if you have this output sequence and the prediction here, then DSER would mark this as correct, even though the dialogue act is different, but it identified that this is an end of the utterance, so it gets the boundary correct, versus here, they're all internal, and the boundary of the utterance is actually here, but the output didn't get it, so it doesn't get it. And then the last one, both the output matches the prediction, so it gets it counts this as correct. Versus in this case, in DER, you'll have to also get the dialogue act correct. And then in WER, basically, we're trying to see this will become clearer. The motivation for it will become clearer when we look at the ASR case. So if you don't have correct words sequence, we would like to see how well it still does in terms of basically dialogue act classification. So here it doesn't get the correct dialogue act because the dialogue is different. But if we merge, so let's say here, if you merge the utterance here, that the sequence is still NY, SV, SD. And if you merge everything in the utterance, you have B, SV, and SD. So this measure is more lenient in terms of trying to get what is the correct sequence of dialogue acts, as sometimes that maybe in certain dialogue system, that's more what you care about. Maybe you only care about what happened, what is the true sequence, but you're not so. You don't really care so much about where the segmentation is. So this measure, it's kind of addressing that. So the results we have here, so this is all models. All models here, we are using the sequence model with BERT embeddings with a history of 1 or history of 3. So the naming is kind of bad here, but history 1 means no previous turns or context was used, and history 3 was in addition to this current turn. We're using 2 previous turns to identify, to do this joint segmentation and dialogue act recognition. So the first set of results here is that when you add context in both the transcript case and the plus prosody case, the error for all of the cases is lower as expected, as you get more context in the history to help with the prediction of what types of dialogue act labels you have. And then another interesting result is if you add prosody, whether it's just current utterance or with 2 previous turn contexts, using prosodic features helps relatively more in the segmentation measure. So you get more gain in using prosody in the segmentation in the task of identifying segmentation versus identifying the correct label. So we think that this is happening because if you have a sequence of turns or utterances, what's being said in the previous turn is already helping signal what should the next turn be. For example, the canonical examples for the pairs, or I think in dialogue literature it's called adjacency pairs, is when you have a question should usually follow a, it should usually be followed by an answer. So maybe yes, no question, yes, no answer, or back channel and agreement could also follow some sort of, in one case, a statement versus a question again. So we think that because of that, the history, whether you, even if you just use transcript, the history plays bigger role in identifying what dialogue act is being recognized. So in the two measures of the correct labels versus the prosody and speech features are more useful in identifying where the boundary or where the segmentation of these utterance are. So this is an example where we have, and this is the one where I said it's pretty quiet. So I'll try to play this. This is the one example where the label sequences, this is one big utterance with, and the dialogue act of it is a yes, no question. If you just use the model with transcript, it incorrectly identified that here is one utterance, and the E% means the dialogue act means is a unfinished sentence dialogue act. But in the prosody model, it correctly identifies that no, there's no segmentation here.
Is your cat an indoor cat or an outdoor cat?
So so my volume's at its max. So I'll try to get this again.
Is your cat an indoor cat or an outdoor cat?
So yeah, how? Thanks, Hal. So I think that this is because of a short pause that that the prosody correctly identified that no, this pause is not long enough for it to be a separate utterance, and therefore it's correctly ignored the segmentation here.
Is your cat an indoor cat or an outdoor cat?
So then another example here, it's also kind of a short pause along the same line, where the transcript thought that this was a boundary, but again, the short pause in the prosody model correctly moved on, basically.
I was just like, I'm wasting my time. I was just like, I'm wasting my time.
And it's relatively quiet. I think this is both the issue of having the pause short enough, and there's also no kind of pitch reset that's often associated with the new utterance. So again, fun examples to show that prosody helps in natural language understanding task. So again, some summary here, again, that we have the neural model with BERT embeddings and longer history here helps with segmentation and dialogue act prediction. And when we add prosody, it seems to us like the prosody model mostly benefits at the segmentation part of this problem, while longer context benefits recognition of the specific dialogue acts in the utterance. So here's another good point for question. If you have any, feel free to unmute yourself. Yeah, I see a hand, yeah.
Hi. Yeah, you spoke a little bit about the segmentation within an utterance, but I'm a bit curious about where the timestamps were, where you're getting the timestamps from for the utterances themselves. Was that just from the annotations in Switchboard?
Yeah, so this was, so again, this here we are still dealing with assuming that we do have annotations of these timestamps, yeah.
Okay, do you think, I mean, I've been doing a little bit of work with Switchboard, and I find that the segmentations that they provide, I mean, I think they were mostly based on acoustic features, like trying to make sure there was pauses, appropriately length pauses on either side of the utterances. did you guys do any work on how the segmentations behave when you have different, when you provide different word sequences?
Well, yeah. So actually, that raises another issue. So I'm assuming you're using regular switchboard. So there's multiple versions of switchboard. There's also the Mississippi State switchboard, which is a reannotation project that they provided some correction to the original switchboard data set with I think better timestamps as well, where people actually, I think parts of it was manual and parts of it was run through a force aligner. We did some heuristic to align those two data sets, where we brought over the timestamps from that Mississippi State data set into our Dialog Act prediction data set. So that's one of that. I think there's also switchboard NXT that maybe you've already heard of it. There's also, so the timestamps could also be from that data set. But in our case, I guess to answer your question, this is some sort of heuristic trying to align this better annotation.
Okay,
Yeah.
interesting. Yeah, that was just a very practical question. I had one more about when you were providing history, you said you provided kind of previous turns. Is there, or were those speaker turns or were those utterance turns?
This were speaker turns. Actually, sorry, utterance turns. So a turn, we defined a turn by just based on who, so this was based on the Dialog Act data. So in each, it's the turn was, I think it's actually based on, well, in essence, it would be based on speakers. So you have A, B, and so on, unless there's some crosstalk. So then there's also practical merging of the next segment to the previous one. So in short, I think it's still based on speaker. Yeah.
Okay, super. Yeah, I was just really interested in how to deal with encoding the prosodic features for these previous turns when we're dealing with speaker change, or whether you found any issues there or ways around it, or like whether you flagged that this was a new speaker, so they might have like a different style or different prosody that would be expected.
Oh yeah, so I didn't show that in the model, but one of the features that's also in the Dialog Act model is the relative speaker encoding. So essentially, you encode whether there's a speaker change with that associated with that utterance or not. So like 0 for same speaker versus 1 for this is a new speaker speaking. Yeah.
Okay, interesting. Great, thank you.
Yeah, thank you. So now we also looked at the effects of not having perfect transcripts. So in this case, we look at how would our systems for both parsing and Dialog Act prediction perform on automatically recognized speech data. In this case, we were not really looking into the ASR system, what kind of ASR system does best in itself, but we were more curious about just given a general output of a typical ASR system, how does it do? So for that, we use we just chose a Kaldi Aspire model because it was open source and most of my pre-processing was already in Kaldi, so it's more of a convenience thing. So the Kaldi Aspire model has a reported 20% word error rate on I think this was trained on Fisher, and 20% was on the switchboard that they reported. So we, for parsing, we retained the 10 best hypotheses. And at this time, the time alignment we'll have is from the ASR output. As I think most of the ASR systems, depending on which you're using, but most of them do provide time alignments on the word level. So so that's good for, again, extracting the features that we have been using for both of these models. And so for evaluation, it will have to be slightly different because for parsing, the tuples of labeled start and ending index of the constituents will require alignments, perfect alignments between the two word sequences. So because of that, we use sparse eval, which is a slightly modified version of the typical parsing evaluation metric. And then for the dialog act prediction, we use the labeled error rate, which I talked to earlier, because once you merge these utterances, then you can kind of avoid the problem of not having the exact same sequence of words. So this is one way of getting at how we're doing the dialog act prediction. So for the parsing, the results here we present here is, so if you just use the one best ASR hypothesis, the result is pretty low. And then the parse score is just using rank the 10 best hypotheses and choose the sentence with the best parse score, whether it's the model using just transcript or the model using Prosody. And then the best ranker is a simple pairwise re-ranking algorithm we learn to train on the 10 best hypotheses, and the ranker will try to select the best one out of the 10 hypotheses, whether it's based on the model with transcript or transcript plus prosody. And the features for the rankers we use is the length of the sentence and some counts of constituents that the predicted parse generated. And then to get some sense of what the oracle is, the oracle F1 is the one where you know the F1 of the sentence, the F1 per sentence, and just select the oracle best of those sentences out of the 10 hypotheses, versus gold transcript is the result we've seen before, where it's a perfect match between the two word sequences. So there's already quite a gap between what you can get from the best F1 in the best case scenario out of the 10 hypotheses, versus if you have perfect transcript. But the result to point out here is that if you use transcript with prosody, you still get a gain, versus even though whether it's just using parse score or using the best ranker. So even with the scenario of not having perfect transcript and just using ASR, Prosody still helps, and in particular in helping to select the best hypothesis in the ASR output for parsing in our case. For dialog act prediction, the results to point out here is that with prosody, you do, so the transcript plus prosody LWR label error rate that we've seen before, there's a drop here. And then with ASR, even with a not perfect transcript using prosody, you still get the help and the result of decreasing error rate. And the notable thing that I like to point out is that the improvement using prosody is even larger in the ASR setting than in the perfect transcript setting. I guess one reason is there's now more for prosody to improve on or to help with, as opposed to the previous case when you have perfect transcript, the pre-trained embeddings is already doing most of the heavy lifting. But now if you in the non-perfect transcript scenario, maybe this is where prosody is really helping. So I guess this is also a point to stop for questions. Otherwise, I'll move on to the current work that I'm doing. Okay, so currently at ICT USC, we're looking at the problem of motivational interviewing, which is a psychotherapy treatment style for resolving ambivalence toward problems such as alcohol abuse. The data we have is a collection of client and therapist sessions. In this case, they're targeting alcohol abuse behavior. So in a typical motivational interviewing or MI session, the data set has a coding of client and therapist behavior. In our case, we're still focusing on client behavior. And it's essentially a three-class classification problem. On the utterance level, we will try to see what is the expressed attitude towards change. So one of them is change talk, where the client expresses willingness to change. Sustained talk is resistance to change. So this is the kind of behavior we want to nudge away from. And then there's also follow neutral is for other types of utterance intents. So this is one example of the conversation. The therapist says, so it's just question for context. Say you talk about drinking about 7 times a week. Does that sound about right? Or something. And then client answers, so this would be marked as change talk because I don't know so much any like 5, probably like the most 4 now. In the middle of the week, I try to just kind of work. So the psychologist annotated this as a change talk for their, I guess, willingness to change. So some indication of moving away from the drinking behavior that they were previously doing. But then this is again sustained talk. So this is where you would need to really look into context, because out of context you can't really say what this utterance means. So this, again, reading it from, I don't know so much any like 5, probably like 4 now. In the middle of the week, I try to just kind of work. I mean, like I would so presumably they're saying, I mean, like I would drink. So this is sustained talk because it's related to what the resistance to change or still sticking to the drinking behavior. And then again, you'll have marked this utterance as change talk for, but it's getting worse, getting up worse, and like being tired and so on. It's an interesting problem just by looking at the transcript itself. A lot of it is dependent on context, and not just the client, what the client said before, but what the therapist said before. So maybe there's other types of questions like complex reflection, where they ask the client to reflect on an instance of drinking, whether it's negative or positive, and that can help elicit what kind of behavior that they want to talk about later. So this is still, I think it's a very exciting way to apply these current models. And so this is just from the text perspective. Once we go into prosody, there's also a question of how to model what kind of maybe. So the interesting thing about this data is that the annotators were asked to withhold any kind of judgment. So let's say if the person says, I think this is pretty bad behavior, I really need to change. So it will still be marked as change talk, no matter how the prosody of that utterance is. So even if they say, oh, I'll change, in a very flippant and not really serious way, it will still get marked as change talk, even though it might not be as there's serious commitment to change or something. So in that data, we also have annotation of follow-up, what they're doing after these MI sessions, and they track whether their drinking behavior improved or got worse over time. So that's what's be one signal that maybe we can use in assessment of whether there are predictive patterns in the prosody that maybe signal sincerity to change, despite what the label said in the utterance of the text-only annotation. So preliminary results based on text only. So this is not my work. This is my colleagues' work at ICT, and we're still working on getting all the time alignments and cleaning up this acoustic data associated with these audio recordings. But there's still a room for improvement with all these, where the F1 we're reaching now, it's 74 for micro F1 and 66 for macro F1 on this 3-class classification. And then the open question that we're exploring now is what type of acoustic features that we're using, whether the CNN module that I talked about before would still be useful. But to use that, we'll need fusion at the word level, where then time alignment, at least some decent time alignment on the word level would be needed. And it's not really clear if we can get that type of quality with this type of data, where the sessions are 1 hour long and there's various types of noise in it. It's just single channel versus split channel, like in the switchboard. Or different kinds of really practical real-world problems in the audio data. So yeah, so it's exciting work with applications in the clinical domain that potentially Prosody could be an interesting aspect to ask even more interesting questions. So in conclusion, my thesis work mainly involved using neural models, in particular the CNN encoder decoder plus the pre-trained embeddings to show the improvement on two language understanding tasks in particular spoken language understanding. We showed that using Prosody gives gains over the already really high quality pre-trained embeddings that are popular in NLP literature. And in particular, Prosody seems to be helping most in disfluent regions, therefore reducing attachment errors, and in the dialogue act case, mostly in segmentation error. And we showed that even in imperfect transcripts like ASR transcript settings, Prosody still helps. And there's interesting takeaway regarding the conversational style of Prosody is different compared to red Prosody, and therefore maybe it's more useful or in general for better learning, training conversational systems, and talk a little bit about clinical application. Thank you.
Great, thanks. Anybody else have questions? We're slightly over time, but I have two quick questions, if that's okay. So have you actually looked at the data set and maybe you can get a rough estimate of the number of examples that can actually benefit from using Prosody?
So it's also, so I'm looking at the current data set, the motivational interviewing data set you said?
No. So this can be applied to any data set. So switchboard, for example. You can randomly sample a few utterance and see whether you can parse just based on transcript, and then whether you get any gain by listening the actual audio.
So I myself have not done that. This is mostly post hoc, looking at what the results we have and then try to understand where the model is helping. But I guess another issue with this is that the tree bank, the reference parses were done by annotators without listening to the audio itself. And same with the dialogue act data. So the dialogue acts were actually annotated without listening. And then there was a later project by that dialogue act data set. They went back and they did listen to the dialogue acts, and what changes most was from agreement to back channel or vice versa. So those are the most confusable pairs. But then I think what they concluded was that the changes were small enough that they didn't re-annotate the switchboard dialogue act data set that everyone's using now. So it's the gold label themselves were not done with listening to the samples.
Yeah, so I mean, it feels kind of sad because there are not actually that many examples that would benefit from using Prosody, at least in switchboard, but maybe in some other domains it will benefit more. Okay, maybe I can squeeze in another.
Just, oh, sorry. Sorry. Thanks. I have a question, but it's a little bit general. It's not really related to the talk. I'm just quite curious. You started your presentation with a number of great examples of showing the prosody, but those examples were mostly text-based, so you have a perfect written sentence. And I think your talk looked at how messy this speech is and how little data we actually have for speech. So I'm actually quite curious if you know, perhaps can elaborate a little bit on whether the situation is the same for written text, and whether you know what kind of data sets are available there. If you were just to look at, for example, predicting the prosody in a written text, just ignoring the speech completely, just focusing on just the written text, and how much we can learn just by looking perhaps at the written text. Thanks.
Yeah, thank you. You mean like written prosody, like if you capitalize all letters or having punctuation, that kind of thing?
Yeah. Because I think each of us probably as a kid read a book with perhaps markers helping us to understand where, for example, the intonation should be placed, and we, as I imagine, can infer quite a lot of prosody from the surface form. When we read it, and you give quite a lot of examples where, for example, you can't really determine what the accurate prosody should be without looking at the context and the context itself. And just if you look at the regular written text rather than at the spontaneous speech, which is really not very structured, ton of problems, if you were just to consider prosody, perhaps annotation detection in a quite canonical, say, English, are there any resources, or is there anyone looking actually at perhaps removing this spoken, say, part from the prosody and just focusing on the text itself?
I'm not familiar with work along that line, but I think so most of the stuff that I talked about is focusing on prosody for like NLP and spoken language understanding. But I think the type of prosody that you're talking about would be very interesting in like in, for example, audiobooks, when you try to synthesize speech that's lively. And so it would be more on the TTS side. And I should say, when I said the stuff about limited use of prosody, it's I think it applies more to the understanding part versus the generation or the synthesis part. So I think, and we'll have more people talk about it in the later seminars, how prosody is important in speech synthesis. But for understanding, I think the focus has mostly been on just the word sequence itself. So naturally, people try to even avoid those types of variations or signals that don't really give you information beyond what's in the content. But yeah, I guess I'm not really answering your question about
no, thanks.
Not familiar with work in that area, but it would be for probably very relevant for synthesis.
Thanks.
How you said you had two quick questions?
Yeah, the second one is whether you have used Toby directly as features.
I have not, but so this was based on, I didn't present this, but this was compared to Mari's previous students' work on using Toby directly. And it improved. There was some improvement, but that was still quite small. And the setting was also different. So the using Toby, I think, was mostly studied in the parsing. I'm not sure if there's Toby studies with dialogue act prediction. But in parsing, the settings is also a little bit different, where again, it has been shown to be more prosody, or those Toby markings or predictions were more useful with the segmentation. So when you don't have known segment errors, when you don't have known segment boundaries, having that prosody helps a lot more.
Yeah, I have some thoughts along the line of extracting Toby from speech and whether you can do it consistently, because I've heard that the consistency among Toby labelers is surprisingly low. Not, I mean, it's lower than, for example, transcription.
Yeah.
So maybe there's some variability that we just don't agree on.
Yeah.
Yeah. All right,
But
I think we're way over time, but this is a really nice talk and nice discussion as well. But if you have many more questions, feel free to email me or Chang's, and I'm pretty sure she'll be happy to answer them as well. All right, so next time we'll have Benjamin, and he'll be talking about speech representation learning. So I'll see you guys in 2 weeks. All right. Thank you, Chang. Thanks, everybody.
Thank you very much. It was a very nice talk.
Thank you. Thank you for coming. Thanks, Hal.